Okay, so we are recorded now. So hello once again officially. So Vincent, first of all, welcome. Thanks for joining. Thanks for accepting our invitation, and it's our pleasure to have you with us and to hear about Classiq's technology. And yeah, I hope that our participants will enjoy the talk. So if you are ready, the Zoom is yours, and we can start. And maybe
Great.
maybe just one question about about asking questions by participants. Would you like to make this session more interactive so that people can interrupt you and ask questions, or we can also ask them to ask the questions on our chat, and then we can just do a Q&A session at the end?
People can ask them
Okay,
straight away. Feel free to come off mute and ask
perfect,
whatever you want. I don't mind. It's always nice to have the questions right away to make sure that uh,
perfect.
we can
All
answer
right.
them directly.
Okay,
So,
fantastic.
so firstly, thank you so much for having us. I'm very excited to be here. And my name is Vincent. I work at Classiq Technologies in Amsterdam, where I'm a business development manager. And my idea for today is I'll show you what the Classiq platform is and what's so special about it. And hopefully some people already created an account at Classiq. And then today we can actually do some hands-on coding during this hour to show you the power of the Classiq platform actually. But before we do that, let's get started and show a little bit of what is Classiq. So firstly, some notes. We see ourselves as a leader in the quantum software industry. We're roughly with 60 to 70 people at the moment. We're headquartered in Tel Aviv with offices in Europe, Japan, and the US. And we both have a large list of enterprise customers as well as education and research partners. So we are very active in basically all spaces in the quantum industry. We are not doing this alone. So we work together with a lot of different partners, ranging from hardware providers like IBM to simulator providers like, for example, NVIDIA with their very large clusters, but also research centers like the Fraunhofer in Germany, and also universities who are using our platform for teaching. So, for example, at the Technical University of Munich, the TUM, they're using our platform for teaching. And we're also, of course, working actively with HPC centers, for example, with an integration from HP. So we're not doing this alone. We're really working together with the entire ecosystem to enable anybody to become quantum developers using the Classiq platform. So what is Classiq? Classiq allows you to design quantum algorithms on a very high level. And once you've designed those algorithms, Classiq will actually optimize and create a logical circuit out of that. So this might sound a little vague now, but let's get started on what we do and how we do it. So before we do that, let's take a look at why we're doing what we're doing. So we see a big challenge in creating quantum software. So currently, the quantum computers aren't that big, both in the numbers of qubits. So the numbers of qubits aren't that high, but also in the fidelities. And because of that, the circuits cannot be too complex, which are executed on quantum computers. However, we foresee a world where the fidelities are higher, where we're maybe even going to logical qubits, and where the number of qubits are also a lot higher. And when that is the case, it will be impossible to program quantum computers in a very low level language. Imagine having thousands of qubits available to you and you manually having to code all those qubits in blocks or in low level gates. That will be simply impossible. So we were thinking we need to do something about that. We need a way to describe the functionality of the circuit and enable that functionality into a logical circuit. So what we did is we looked at also how this is done on a classical computer, where you also have a high level code. Nobody's coding in very low level languages anymore. Where you have a high level code, you have a high level description of what you want, and a compiler or something will actually create the low level code for you. And it will create that low level code for each specific device, because that is something very important as well. Each device in a quantum space is completely different. So if you want to optimize for each device, you might need to rewrite software for each device. And we don't want that. So what we have done is create the first high-level language, which is able to, which allows you to describe your functionality in a high-level language, and we will synthesize that into a logical circuit for any type of quantum computer. So you never have to manually code any gates anymore, or have to decide how should I implement this functionality, because that is actually what our synthesis engine will do for you. And with that abstraction comes a lot of efficiency and a lot of scalability. We're able to create circuits from either tens of qubits to hundreds of qubits to thousands of qubits and even more. And also in terms of depth, we can create circuits up to millions and millions of depth. And every time we synthesize a circuit, we take into account the target that we're synthesizing for. And with that, we create the most optimal circuit for that target. So you never have to rewrite your circuits when more qubits become available or when you want to target a different device. So that is what we are offering. And as I already said, so what we do is with our high-level language, we allow a lot of abstraction. And this isn't just great for scalability, but this also opens up the world for other people to program quantum computers. So you don't have to be a PhD in quantum information theory to use quantum computers. Our high-level language allows anybody to create software for quantum computers. And also with our built-in packages, you're able to quickly get started without being a PhD in quantum information theory. And with that, we really make it a lot more usable. So you don't need to be both very knowledgeable in your field of expertise and on quantum information theory. You can be a chemist and use our packages to do your calculations without knowing in detail what a quantum computer does. Or you can be a financial analyst and get the price of your option, for example, without knowing how a quantum computer works. And that is really what we're trying to achieve with our level of abstraction. So how do we do it? So firstly, we have the model. And this is one of the most important things. And this is what we use to describe the functionality of the algorithm that we want. And we have two ways of programming this model. We have a Python SDK, which is, I think, the most commonly used language to program quantum computers. So we have a Python library which does that. And it's very different from the Python libraries you're probably used to, like Cirq or Qiskit, because it doesn't use this concept of low-level gates, but it uses a lot more high-level abstract modules, which allow you to describe the functionality that you want, and we will make a logical circuit from that. The other side is an online IDE, and this is something we will be using today, and that makes it very easy for basically anybody to program any code, even if you're not a Python developer. So it's a really low-code approach to programming a quantum computer. So this model is very important. It describes the functionality that we want. So if we want to go from our high-level model to a low-level logical quantum circuit that we can execute on a quantum machine, we synthesize that model. So we go from that high-level description into our synthesis engine, and that synthesis engine will create a logical quantum circuit. So it's very important that the synthesis engine takes in two parameters, basically. One is the model, and the other one is the description of the target that you have. That can be either a simulator or that can be an actual quantum computer. And the interesting thing is, if you want to target a new quantum machine, you will never need to reprogram the model. The only thing you need to do is tell the synthesis engine, I have this new quantum machine as a target, and I want to use that. I want to use that target. And the synthesis engine from scratch will generate a new logical circuit to actually implement that model's functionality on that quantum computer. So it could be that the logical circuit you get from one device can be completely different than a logical circuit from the other device. And that is really where the power of Classiq lies. If you want to have efficient circuits, you do not need to reprogram them completely. So we go from our model, we synthesize it into a logical circuit, and then we have our visualizer. Our visualizer is basically an analytical application which allows you to see, what does my logical circuit do? What functional blocks do I have? And how are my functional blocks implemented? As you might know, in a quantum computer, it's possible to implement your functional blocks in various ways. Not all functional blocks have that, but for example, adders or other things, there's a lot of different ways how to implement them. And our synthesis engine might choose a specific implementation for one machine versus another implementation on the other machine. And in our visualizer, you can really easily see what type of implementations has been chosen for this specific machine. The output of this is any type of output you want. So that can be QASM, it can be Cirq, it can be Q#, whatever you want. And with that, it allows you to also execute the logical circuit that Classiq creates on any gate-based device. So we can quickly send it straight to AWS, Azure, or any other universal gate-based quantum computer, either straight from our visualizer application, or you can export the QASM code and execute it on the machine yourself. So we have a very free and very flexible way of executing what we do. So how does our SDK look like, our platform? So as I already said, we have two interfaces. So we have a Python SDK and we have an online low-code browser-based IDE. And the last one, so the IDE, is something we'll use later today. So to start modeling, to start creating your model, you have building blocks, algorithm building blocks, which are predefined, and you can use them to create your own larger algorithms. For example, if you want to do HHL, you need some state preparation, you need QPE, and your other steps. All these different steps in your algorithm are already built in, so you can use them. You can create your algorithms completely from scratch. So we allow you to have your own user-defined functions within an algorithm. So maybe you have a different implementation for a function and you want the synthesis engine to use that, or you have other things that we don't have. We allow you to extend on the built-in functionality that we already have. Next to that, we have completely ready applications for you, which you can directly use. For examples in the field of finance and chemistry, you don't need to program anything yourself. You can directly get started with with option pricing or finding the ground state of molecules. And with that, once you have modeled it, you can synthesize it for either hardware that we already have in our system. So that can be IBM machines, IonQ machines, Quantinuum machines, whatever. But you can also bring in your own machine. So maybe you want to play around with what would an algorithm look like if there was a specific machine with this native gate set, or there would be a machine with this connectivity. How would my logical circuit look like if there would be changes in those parameters regarding native gates or connectivity? All those things you're able to freely experiment with within the Classiq platform, because we don't have any fixed targets, so you're able to play around with how would that look. You're even able to play around with what would happen if my hardware would have a native CCX gate. Would my depth decrease a lot, or how would specific blocks be implemented. So this is a lot of freedom that you would get. Once you have your model, we have a lot of different analysis tools, from resource management to qubit mapping to comparison between various hardwares, etc., etc. So you really can see what is happening when you're creating this quantum circuit. And then, as I already said, you're able to execute it on any type of device, whether it is directly through the cloud, for example, via IBM, AWS, or Azure, or maybe you have your own quantum computer in the lab where you want to experiment with. You're able to execute this logical circuit into QASM or Q sharp and use that to actually execute your circuit. So before I move on, let me pause a little bit. Maybe there are some questions already, and otherwise I will move on.
Okay, let's see. I don't see questions here on our chat, but maybe someone would like to unmute and ask. So just to let you know, we agreed with Vincent that this session can be interactive, so you can also interrupt and ask questions. Maybe I'll ask one question because
Sure.
there is one question from Ivan. What about QML? So I believe quantum machine learning.
Yeah.
I think it's also covered.
Yeah, so we already have built-in QML algorithms. So if for example, in high-level modeling, we already have things like quantum neural networks or quantum support vector machines. They're already built in. So if you would like to explore quantum machine learning, we already have built-in building blocks for you to actually leverage that. Yeah.
Okay, so I have one more question regarding the hardware and the approaches, because I can see that there are just universal gate-based quantum computers. Do you also expect to integrate Classiq with quantum annealing technologies, like from D-Wave, for example?
At the moment, not. At the moment, it's really gate-based device.
Okay. There was a question from Jonathan. Can we integrate your visualizer into our game? So I believe that the game being developed now during the hackathon.
I mean, why not? So you're able to send any QASM circuits or anything to visualize it. So feel free to use it. That will be great. Sure.
Okay, that's very nice. All right. Do we have more questions now?
Okay.
I think
So in
we
that
can
case,
go on.
sure.
Yes.
So in that case, let me show you how it actually looks. So this is an example of what we use. So this is a little bit older code, but and it shows you how you could create a quantum circuit. So on the left, you see we have some constraints. These are the hardware constraints, in this case, the number of qubits. And also we can tell our synthesis engine, what do we want to have? Do we want to have a circuit which uses the least amount of qubits? Or do we want to have a circuit which is the least amount of depth? So in this case, we say we want to optimize for depth. And in our logical flow, we have the actual functionality, so the functional blocks of our algorithm. In this case, we want to have an arithmetic oracle, so a Grover oracle, which solve a specific arithmetic expression. So we have various variables, so A and B, and we want to find the values for A and B that satisfies this mathematical expression. So when we synthesize it, the circuit on the right could be something that would come out of this. And this is something we'll see later, but it's very easy to go from a high-level model to the right. And every time you would change the constraints to a different type of hardware or anything, the circuit on the right could completely change based on the characteristics of that specific machine. So this is some examples of our of the analytics tools. So we have hardware comparison. You can see how the qubits are mapped, how the resources are used, so how the various qubits are used. So maybe one qubit is used more than others, etc., etc. Some examples on the execution. As I said, we can execute basically anywhere as long as it's gate-based. So going back to the question, at the moment, unfortunately, we're not able to target any annealers. However, we are able to very easily solve a lot of optimization problems. We have a very strong optimization suite. However, this is done on gate-based devices and not on annealers.
Mm-hmm.
This is a small list of applications that we have ready. So, for example, portfolio optimization, option pricing. We have various things around cybersecurity, HHL, which can be used for anything. So you can do financial modeling. However, you can also do CFD or solve any set of linear equations. We have credit risk analysis, and as I already said, quantum machine learning. So both neural nets as well as support vector machines. So let us see one of the examples that we're doing together with customers, because it's very nice to have this platform, but of course nicer to have it being used by somebody. And one of the examples that we're using is Rolls-Royce. Rolls-Royce makes airplane engines, and to make those as efficient as possible, they're using a lot of CFD, so computer fluid dynamics, which basically models the flow of air inside of such an engine. And this is a very computationally intensive process. So what you want to do is you want to see, are there parts of that that can run on a quantum computer to speed up that process. And as it turns out, a part of that CFD workflow can be mapped into a set of linear equations. And this is very interesting because to solve a set of linear equations, we can use HHL. And the nice thing about the HHL algorithm is that HHL has an exponential speed up. So this is very interesting because that is something that we're looking for in quantum algorithms. We want a very high speed up because then we have a large advantage over classical computers. And that is what HHL can give us. So this is an example that we've done with both Rolls-Royce and NVIDIA. So we have created a circuit with over 39 qubits, if I'm not mistaken, and a depth of into the millions. And we have executed that on a cluster of NVIDIA, so a huge GPU cluster. And as far as we know, this is the biggest quantum circuit that has ever been executed. So that was very cool. We're using this as well in education, as I already said. And Carnegie Mellon, which is a university, is actually already using our software to teach new students on how to program quantum computers. So with that, final check if there's any questions, and otherwise we will go to the workshop. I see one question in the chat. Any compiling going on? Well, it's not really compilation. What we do, we call it synthesis. And how we do it is it's very comparable to what is done when you would create hardware. So if you would design a CPU, for example, you would describe the functionality of that CPU in a high-level language, for example, VHDL. And then a synthesis engine will take that VHDL and will actually create the logical circuit for a CPU, which is basically a large set of gates. And that is the same type of process that we also use. So we also have a high-level language and then eventually create a set of logical gates. And because we're using that is one of the processes that we use. So it's a bit different than compiling. And it is very different than transpiling. So traditionally, when you create a circuit, for example, in QASM or in Qiskit, and you want to transpile it from an IBM machine to an IonQ machine, this is possible. However, that transpilation doesn't change the logical circuit. So it tries to fit the logical circuit to a different machine. And what we do is we create a new logical circuit specifically for each machine that you target. And with that, you could get a lot of increase in, for example, depth, so a lot of decrease in depth or the numbers of qubits used. I hope that that makes sense, Ivan.
Mhm.
Um, Another question, what are other applications used in the field of quantum machine learning that can be easily proved advantage compared to classical? As far as I'm aware, there hasn't been any formal proof that quantum machine learning has an advantage over classical machines. As far as I'm aware, there are studies which show advantage not per se in the speed, but in the amount of training data used. So a quantum machine learning algorithm might need less training data compared to a classical one. However, as far as I'm aware, there's not yet a proven speed up or something like that in the quantum machine learning compared to classical machine learning. And to be honest, this is going to be super tricky because what we're
Mhm.
doing now with traditional machine learning is extremely efficient with the large CPUs and everything. So it's going to be a big challenge for a quantum computer to beat that.
I think that this HHL algorithm that you mentioned is the one for which the advantage is expected. I'm not sure if it
Yes,
has been proven,
it
but
is.
at
It
least
has.
it's okay. So at least it is expected. It can be applied in quantum machine learning as well, but not
Yeah.
explicitly to, let's say, train deep neural networks or so on. So it's we can't expect that for sure there will be some breakthroughs that will change the world due to usage of quantum computing in this particular domain, but there might be some small improvements. As you said, I also heard about some papers in which by adding some quantum layers to the neural networks, some researchers were able to obtain a small advantage in terms of accuracy of detecting some objects or images or something like that. I think there's a question from Victor.
Okay.
Yeah.
Go ahead.
Can you hear me?
Yes.
Yeah. Okay. So yeah, I don't understand. You mentioned that at the end you have a logical circuit, no? But
Yeah.
at the end of the day, you are going to send this to the IBM, Quantinuum, whatever, and there is
Yeah.
going to be a transpiler for IBM, for Quantinuum. So at the end of the day, the depth of the circuit is not going to be the same as the one you are sending, no? Or
We can do the transpilation ourselves. So we can transpile it directly for that machine. So you'll see later our output. So if you look at the statistics for the circuit that we're going to send to the machine, you have the statistics for that specific machine. So the depth that will be executed on that machine and the gate counts, etc., etc. So um, if you send a logical circuit that's not transpiled, then yes, IBM or Quantinuum will transpile it for you, but you can also do that yourself.
so in the example that you show that you can optimize the depth or the qubits, in this
Yeah.
example, is the transpire circuit already? Or
No. So we optimize the logical circuit for a specific machine. So when we would say, for example, so if we compare IonQ to IBM, a difference would be the connectivity between the two. So it could be that IonQ has all no connectivity, whereas IBM has a different type of connectivity.
Mm-hmm.
If we have an adder in that circuit which adds two registers together, there's various ways how to implement that adder. You have a ripple carry adder, you have QFT adders. And one thing we do is, for example, if we would target an IonQ machine, is say, well, we're going to pick the QFT adder because the QFT needs a lot of connectivity between the qubits. So that is very interesting. And if we would transpile that, we have a very short circuit. And also the logical circuit is relatively short. However, if we would implement that on an IBM machine, and we would transpile QFT on their machine, we would introduce a lot of swap gates and other gates to make that QFT work because the qubits aren't all non-connected. So that is one thing. That would happen if you won't change the logical circuit and you would take the same logical circuit and transpile it to IonQ and to IBM. What we would do is we would take the same functionality, so that adder, and we would then look is there a different implementation possible to make it more efficient on an IBM machine? And so there is, for example, you can use a ripple carry adder, which needs less connectivity between the qubits, but in a logical circuit, it has more depth. But after transpilation, the ripple carry adder could be more efficient on an IBM machine versus the QFT adder. So that is what we do. So we change the logical circuit per computer. So a IBM computer would have a different logical circuit than an IonQ machine, for example. And this is really the big difference between transpilation, because at transpilation, you always keep the same logical circuit and simply transpile it to each machine to make it work. So that is the big difference. Does that make sense?
Yes, I think so. I think so. But for example, what the thing I don't understand, does your results compare with the transpiler of, for example, IBM? No, I know that Qiski runtime offers a service where there is an optimization of the transpiler. No,
Yeah.
that they are saying that if you send something here, we are doing the optimization for the best optimization that we can do in the transpiler, given the circuit that you have sent, and also depending on the calibration that we have that day, etc. No?
Yeah.
So how does your optimizer compares with that? For example, I understand in IonQ, because IonQ doesn't have like something so refined as IBM, no, for the transpiler. But in the case of IBM and other companies, how does the results with your optimizer compares with the results of the company, you know?
No, I completely understand what you mean. So I think the big difference is, as you already said, so you said you send your logical circuit to IBM and the transpiler will optimize that as best as it can to fit that hardware. What we do is we make that logical circuit more efficient. So if you, as a human, are not able to make the best possible logical circuit for that machine, we can help you with that. And we can help you, and we can create more efficient circuits by adding auxiliary qubits, reusing auxiliary qubits, choosing the right implementation for some specific functionality. And after we created the most optimal logical circuit for either IonQ, IBM, or whatever, then the transpiler can do its job as after we have created the most logical circuit. So the transpilation and the synthesis that we do are two completely different things. We are creating the most optimal logical circuit for each machine. And then the transpiler is trying to make that even better, basically. But because we are already having an optimal circuit for that machine, the transpiler probably needs to do less work.
Okay. I think I understand now. Yeah. Thanks so much. Hey, I have another question. I don't know if
sure, go ahead.
we have time. Yeah. So you offer you can run the circuits in your system, right? Like you have a simulation of your system, right?
Of course. Yeah. Either with us or you can run it on IBM. Yeah.
Okay, so you offer your own thing. So do you have like noise models and also no? Okay. And
no.
For example, error mitigation at the moment of you want to send something to a actual hardware. Do you offer something related to optimizing no?
No, that is something the hardware providers do. So we create the best logical circuits, and error mitigation is being done by IBM, IonQ, or maybe Q Control. They know the hardware better, and we are really focusing on creating the most optimal logical circuits.
But for example, zero noise interpolation and all those kind of things, like it needs to be like the parameters needs to be like optimized, like even in the logical sense, like to understand exactly how to use the parameters in your circuits for certain methods of error mitigation, no? And even before sending to the actual hardware, no? So in this case, you only offer the perfect simulation, the perfect logical circuit, and then that's it, no?
Yeah.
Okay.
Yes.
Okay.
Yeah. At the moment, yes.
Okay, sounds good. Thank you so much for the answer.
You're welcome. I see one more question from in the chat, and then I will actually go and do the demo. What's the main problem that we're facing to prove advantage? It's not really that we're facing a problem to prove advantage. It's more that we don't have many algorithms that actually have advantage. So mostly, maybe it's good to have, for example, check the big O notation on Wikipedia, which shows you the difficulty of a circuit. And there are circuits which are proven to be less resource heavy on a quantum computer compared to a classical. However, we don't know that many, especially exponential speedups. So we know Shor, we know HHL, and that is as far as I know, one of the few. And there are others which have quadratic speedups, like Grover. But then the question is that enough to actually have practical quantum advantage? So proving speed up isn't really the problem. The problem is getting algorithms that have that advantage. So Jonathan asked how to use SDK, how we can contact you. I think via the organization is the best way. Okay, so with that, what's the biggest data set I can use with an Oracle, like gigabytes? Well, I think that will be a tricky, because I think you would need a lot of qubits to do that. So I think that we're not in the gigabyte range, yet. Okay, let me switch actually to my other screen and actually just show you a demo which you could follow along to if you would like. So this is so I get one more question about, are you going to include the supporting hardware the new quantum cloud offers on 136 qubits? So, oh, I'm not opening your link. So the idea for us is we are basically able to support anything. We're not supporting everything directly from our service, but as you'll see later, you're able to grab CASM or SIR code from that thing that you created, and you can execute it on them yourself. So that's something I'll show in a little bit. So firstly, what we're going to do is I'm going to show you how it works, and then ask you some interesting challenges. Let me see. Okay, here we go. So this is a Classiq platform, and I hope some of you have signed up. And if you haven't, then please go to platform.classiq.io and use the sign up. I'll put it in the chat as well. And what you can actually do is you can start synthesizing your first quantum circuit. So how is that done? So we go to synthesis, and we have some pre-made things for you set up. Let's start with the state preparation. So also the questions on the oracles and with the gigabytes, you need some sort of way to encode your gigabytes of data, or let's now start with just bytes of data, into your quantum logical circuit. And mostly that is done using a state preparation. And this state preparation is a very simple state preparation because we're using real and positive probabilities on the basis states. So what does that mean? In this case, we have 5 qubits, and qubit state 0, 0, 0, 0, 0. We want a probability of 0, and a basis state 1, 1, 1, 1, 1. We want this specific probability. And a state preparation in a quantum circuit is mostly an approximation, because the closer you want to get to your actual state, the deeper the circuit will get. So, and if you don't have that much fidelity, you might want to give up a specific amount of depth to make sure then you're not as close to the real state that you want, but at least you don't need that much depth. So we can specify that in our error metric. There are various error metrics that we can use, and this is our current error budget. And the rest, we have some classical parts of our system, which says that we are just sampling the results in the end, and we want to have an histogram. And lastly, we have some constraints. So we say we don't want to use more than 5 qubits. Our max depth is 1,000, and we want to optimize for depth. So the only thing we need to do now to actually get, and in this case, we'll lose this for a bit. We'll use that later. We can say synthesize. And with that, we will take this high-level description and we would actually get a logical circuit that implements this. So we would get, this is the logical circuit. We will start in an equal superposition with these H gates. And then using a variety of RY and controlled gates, we actually get to the desired state preparation. So if you want to execute this, for example, on the machine you just shown, you can say export, and you can export it as chasm or as transpiled chasm. And then you can actually execute it anywhere. Ilionis, I will answer your question in a little bit. So I'll get back to you. And we can execute this. So let's start by just executing it on the air simulator, which is hosted by ourselves. And we can say run. It is running now, completed. And this is state preparation that we get. So success. Now, what we can do also is say, well, what we just did is we assumed any as you said, any architecture. So an all-to-all connected architecture with any possible gates. This is unfortunately not the reality. So let's synthesize something for real hardware. So let's say we do an IBM machine, and as a backend, we take Nairobi, for example. And again, we have optimized for depth. So if we now press synthesize, what you will actually see is it will create a completely new circuit with, so initially it looks the same. However, the transpiled gates, which you see right here, is completely different. You see the depth is different. The width is the same because we put it the same. And if you would look at it, in this case, I think the implementation is fairly similar, but how it is, eventually it's a different circuit. So the first question for you is, for anybody who has actually created this, created a account, let's see what would the results be. So what would the circuit information be if you would synthesize this, but then synthesize it specifically for an IonQ simulator? So this is now I've synthesized it for an IBM machine. So what would the results be if you would synthesize it for the IonQ simulator? And so people follow along. I'll give everybody 4 minutes max. And then please, to show that you have completed it, send the depth in the chat. Then I know that people have actually done it. And I'll be quiet for a few minutes so you can actually execute it.
Maybe I will ask just to be sure.
Sure.
Can we ask to raise the hand the people that are following and now trying to build it?
That's a good question.
Maybe. That's a good question because I'm not sure. I know that some people have created the account, but I'm not sure if they have started it now. And So if you are following, then please raise your hand, and if you would like to take this time to prepare this circuit. I don't see any hand raised. Maybe you can also send a message on chat if it's easier.
Oh, I see. Ivan is
I think
following
Ivan.
along.
I think that Ivan is working. Okay. Do we have more people? Yeah, but anyway, if there's only one person, we can wait, and maybe yes,
Oh, okay,
Ricardo.
there's more people following
Good.
along.
Yes.
Perfect.
So yes.
We'll give you a few more minutes and then we'll head to the more difficult
Yeah.
example.
Mm-hmm. All right.
And as of course, if anybody has a question, feel free to ask, of course.
So maybe in the meanwhile, I will ask about potential applications to develop quantum games. Have you maybe heard about any quantum games developed using Classiq technology? Maybe there are already some. If not,
I
then
haven't, to be
yeah,
honest, I haven't heard any examples yet, but it will be very cool. So I'm very
yeah.
curious to hear.
Maybe there will be the first quantum game developed using Classiq here during this hackathon. So
Yeah, that would be
that would be
amazing.
very, yeah, that would be great. So yeah, additional motivation to you guys then. So you can be the first in this, let's say, competition or in this field. So it's also something interesting. Yeah, but anyway, so it seems to be very useful. So yeah, there was already also a question. I think yeah, so Jonathan said that he would like to use this SDK, which is great.
Yeah, so we have a Python SDK also. So for people who aren't following along, you go to Classiq
Yeah.
and here in the Learn More section, you have the Python SDK and you have all the tutorials. So you can basically get started with our user guide. You can get started with basically with our Python SDK which I think is more easier if you're developing a game than our online IDE. Okay, so Ivan and Ricardo, I hope that you were able to actually execute. I've done it as well, of course. So what I got is on the IonQ simulator, the depth was decreased a lot, and one of the reasons is the IonQ simulator has some native CCX gates, which of course aren't there in a real device, but a simulator has. So if we would say now IonQ simulator, and we would say synthesize, you would see actually that the depth decreases dramatically because it has these gates uh, which a real quantum computer doesn't have. So you'll see it has these nice CCX gates, which will be amazing. But unfortunately, there aren't there in real quantum computers yet. So we get this very shallow depth. Okay, now let's do something else. Let's do a
Okay.
Grover algorithm. This is, I think, something that a lot of people are already familiar with. Grover, about speedups. It has a quadratic speedup, so it's not exponentially quicker like Shor or like HHL, but it has a big speedup. And let's also take into the question that there was raised before about the 136 qubits device. So let's say that we have 136 qubits available to us. So we can say 136 qubits in our oracle, and max width in the entire circuit is also 136. If you want, we want to have the shallowest circuit, and what you can do if you want to target that specific machine, so I'm not sure what the current topology is or what the native gates are, what you can do is you can say, well, you can select the native gates here, and you can also create a connectivity map. So then you would get a real optimized circuit for that specific machine. But instead of doing that, let's first just see what we can do. So what we see here on the right is our expression. So this is a mathematical expression. So a plus b plus c, and here this is c bitwise and 6 modulo 4 and 4 bitwise 6. This whole thing needs to equal 4. So we want to find values for the variables a, b, and c. Here also c that satisfies this equation. And Grover is a great way to do that. So the only thing we need to do is write our expression, have the name of have the variables defined. So variable a, we have a size of 2, and we can have it signed or unsigned. We can have fraction places or no fraction places. B and C the same. So the only thing we need to do now is say synthesize. And now, because we haven't selected any backend provider, it assumes all no connectivity and it assumes all native gates. So this is the circuit that we get. They vary. You will start with the uniform superposition, and then we go into our oracle, arithmetic oracle, and our diffuser. So here we go. This is how the oracle is actually implemented. So this is the oracle that we got. So we have the pluses, so the adders, bitwise ORs, etc. And as you can see, it is not a on the left side of the oracle and on the right side are not exactly the same. So it's not a naive oracle. We can optimize it. So that is one thing which is very nice. But now let's see what would happen if we would say, well, we use exactly the same model. So we don't change anything here. And not sure how many qubits this device has, but let's say we want to have, again, depth optimization, and we want to have it for IBM, and we, for example, want the Washington machine, which has a lot of qubits. I'm not sure how many, but a lot of qubits. And so the interesting thing is, how will that actually change how our oracle looks? And this is something which really shows the power of the Classiq platform, because you hopefully see that the actual implementation of the oracle is different than the one which didn't have this specific. And already you can see the depth has changed. Let's see how the oracle looks. Oh, the oracles, I think, roughly implemented the same as here. No, it's implemented differently, and that is because of the connectivity between the qubits and the native gates that are available. As you can see, these are also different. The actual synthesis engine has created a different type of oracle to implement it as efficiently on that device as possible. So now what we could do is say execute. Again, on the air simulator, we can say run, and it will actually run it, and you will get the results. And the last step you would need is some classical post-processing to get the actual values for each variable. In this case, we just see the histogram of the counts for each base state. I hope that we get the result soon. Otherwise, I can just show it. I think this was the best result. So this is the result, and you have to post-process this into getting the integer values of your machine, of your specific variables. So I hope that this was very cool, and I invite everybody to start playing with that. And I mean, we have 4 minutes left, so I hope there are some questions, and I hope you really enjoyed it.
Okay, great. Thank you. Thanks, Vincent, for the great presentation and demonstration. All right, do we have more questions now? So yeah, Ricardo just posted that he has already done the circuit, which is great. So thanks, Ricardo. Any more questions or comments? So Vincent, maybe I will first ask a question regarding maybe help to those participants who would like to use Classiq and have some questions. Can we maybe share your corporate email address, or if there are questions, maybe I can just forward them to you. How would you prefer to?
Both are fine. Both are fine.
Okay, so if it's fine, I think that the direct contact will be best. So if it's fine for you, you can maybe share your email address, or I can do it on the Hackathon's Discord. If it's fine.
Both is fine. I will put it in the Discord. That's fine.
Yes. All right. Great. And yeah, so we'll officially announce that if there are some questions, people can just contact you directly. Good. Do we have more questions or comments? Comment from Ivan. I have done a lot with Q#, Emacs, Lisp, Python, Quantum, and this is the most intuitive. I have my chemistry and other quantum is easier now. Yeah, hopefully.
Great. Yeah,
good
that
to
will
hear.
be amazing.
Yes.
We have some nice chemistry examples also available, so feel free to use that.
Yes. Perfect. Yeah. Acknowledgement from Amrit. Thanks.
Great. Thank you.
All right.
Okay.
I don't see more questions now, so maybe I'll just stop recording.
Thank you.